So Steve, I think I'll start. I'll introduce people and yes, and then I'll hand it over to you.
Okay, thank you.
Okay. So hello everyone. We hope this finds you well and healthy. My name is Eric Wanjao. I am a Microsoft Learn Student Ambassador here in Kenya, and we're really pumped that you joined us in our session today. So actually, this is a series of sessions aiming at getting everyone up to speed with machine learning. So today we are starting at the very basics with regression, one of the simplest algorithms for doing supervised learning. So that may seem dull compared to more modern statistical approaches. It's still widely used, and it's a good starting point for more advanced approaches that we'll take in future, such as classification, to deep learning, to neural networks. Yeah, so we really hope you ride along with us. It will be an adventure. And yeah, so this will how to go. So Steve will start off with a little introduction of what is regression and everything, and then we'll do a lab in Python, and then we'll finish it off with a lab in the R language. So thank you again for coming, and we hope you have a really amazing time. So Steve, I hand it over to you. Thank you.
Okay, so as I introduced myself, my name is Steven Murage. I'm a SLAN student ambassador at TUK in my third year, and I'm also passionate in AI and IoT. So basically, the first slide was to introduce myself and also to introduce the topic that we are covering today. So here's the plan. Like I was to introduce regression, the difference between linear and polynomial regression, understanding polynomial regression, advantages and disadvantages of polynomial regression, and also a Python code walkthrough. So, okay. So about regression, it's a machine learning method which basically is used to predict a continuous variable y based on one or multiple predictor variable x. So you could be having either one column, which you should be using to calculate the value of y, or maybe several others. So basically its goal is to build a mathematical function and also express y as a function of x. So the easier linear regression, the mathematical function is y is equals to fx. So the function of x, yes. So we have various types of regression. First one being linear regression. Second one, quantile regression, logistic regression, and also polynomial regression. So basically, linear regression is used. It's used basically whenever you have data which correlates linearly. Polynomial regression is used whenever the data isn't linear, or the relationship between the data isn't linear. Okay, I'll be covering maybe those two, although logistic regression is used whenever you want to predict whether someone can pass or fail a test. Yeah, basically it's like a 1 or 0 type of polynomial regression. Okay, you can get to the next slide. Eric, get to the next slide. Yeah, okay, thank you. So a question here, what is polynomial regression? It's a form of regression which predicts a continuous value y from an independent value x whose relationship is nonlinear, as I was telling you. So basically that's the definition of polynomial regression. We'll get to see the examples Eric, we can go to the next slide. Okay, here I used various images to distinguish between the two, distinguishing between linear and polynomial regression. As you can see on the linear regression, it's like just a single line, which can maybe be used to predict values whenever you have any value at x. So, and as you can see, the data there, it's like linearly, it's related linearly. So for the polynomial regression, as you can see, it's curvilinear. So there's like a curve. You can't, yes, you can have a linear regression onto this, but you'll not be maximizing the output, and also your predictions might not be that accurate. So the function for the polynomial regression is y is equals to b0 plus b1 x1 plus b2 x2 x1 squared, sorry. Okay, the b0, they are the x values which are changing each and every time. The x is a coefficient which remains constant, except that whenever you're getting to the next coefficient, you'll have to add up on the power. So the first one is x1 raised to power 1. The second one is x1 raised to power 2. So the third one should be x1 raised to power 3, and so on. So Eric, you can go to the next slide. Okay, thank you. So understanding polynomial regression. So as you had said earlier, it's used whenever variables are dependent but not linearly. So it does not require any relationship between the independent and dependent variables to be linear. So, and the equation is there as I had given you, y is equals to b0 plus b1 x1 plus b2 x1 squared plus b3 x1 cubed plus bn x1 raised to power n. So you just continue till you get to the nth power. So also there are various assumptions which polynomial regression checks. One being that the behavior of the dependent variable uh, can be explained by a linear or curvilinear relationship. So, and the dependent variable is a set of independent variables. So like you have an xi whereby I is equals to 1 to a variable or a value k. The relationship between the dependent variable and any independent variable is linear or curvilinear. So it's like I had explained earlier here. So the next slide also continues with the assumptions. So the independent variables are independent of each other. So like whenever you have the x1 or the b0, sorry, the b0 shouldn't be like a function of the next b1 or the b2. So, and also the errors are independent, normally distributed with mean 0 and a constant variance. So okay, thank you. So here is another question. How do you know whether the degree of the equation is right so that you can prevent underfitting or overfitting. So there are various methods. So the basic ones being forward selection, and the next one backward selection. So forward selection means like you'll be increasing the degree value till you get the best possible outcome. And the backward model selection, you decrease the degree till it's significant enough to provide the best output. So there is also some maths behind that. So linear regression is basically the first degree of the polynomial. So as you can see, the first equation there, it's like correlated to the third equation, but to some extent. So there's a point where it breaks. So linear regression, simple linear regression is represented by y is equals to b0 plus b1 x1. Multiple linear regression is y is equals to b0 plus b1 x1 plus b2 x2. So as you can see here, you can note that the coefficient is changing till you get to the nth coefficient, that is. So polynomial regression, um, y is equals to b0 plus b1 x1 plus b2 x1 squared. So the coefficient isn't changing, but only the power is changing. So there's a difference between the multiple linear regression and the polynomial linear regression. So that's the difference. So you can calculate the cost of a polynomial regression model. So the cost function is a function that measures the performance. So in any given data maybe. So it's basically the calculation of error between the predicted values and the expected values. So the cost function for polynomial regression is j is equals to 1 over n. So you multiply that with the sum of the predicted values minus their respective y values, then you square that. So n is a sample. So here I explained the function, or the function that we had given earlier. So as you can see, j 1 over n multiplied by the sum of the square of predicted values minus their respective values y. Yes. So in an ideal situation, the cost function is mostly 0 or somewhere close to that. So if you need to know whether your model is accurate, so the cost function should be close to 0. So there are advantages of polynomial regression. So one of the advantages is that it provides the best approximation of the relationship between dependent and independent variables. So also it fits a wide range of curvature. As we saw, it's like curvilinear. Also, it supports a broad range of function that can be fit under it. So there are also some cons here. So disadvantages of polynomial regression. So if you have any outliers, so the results are seriously affected. So it's sensitive to the outliers. So in addition, there are fewer model validation tools so that you can detect the outliers than maybe linear regression. Yes. So we have some conclusions here to make. So whenever you have any problem, I do start by that. You start by visualizing the data. So if you're given any problem that you are supposed to solve, you first visualize the data so that you can know, do I use linear regression or polynomial or any other model? So you visualize maybe via a scatter plot and you see what's the best to use. So also you noted that polynomial regression is sensitive to outliers and you can prevent overfitting and underfitting in a model. So I gave you two examples where you can prevent that in polynomial regression. So polynomial regression is also part of linear regression. It's only that it's expressed a bit differently. So polynomial regression fits a wider range of curvature. So with that, I have completed my slideshow. So there was the code walkthrough. So Eric, Eric,
Hello, Steve.
so I don't know how to go about.
Hello.
It's on my Azure notebooks.
Okay, maybe I could do this. We can do a little detour because you're supposed to start with the Python part and then the R part. So I could start with a code walkthrough of R and then you'll do the Python one later.
Okay, so you'll start with the R.
Yeah, I'll start with the R real fast and then maybe hopefully you have sorted your stuff or something.
Yeah. Let me try that. Okay, then you can start with the R as I solve this.
Okay. Okay. Thank you so much for the slide. I will definitely use them in my presentation. I refer to them multiple times. So I've just sent the Azure notebook on the
Yes.
meeting chat. So anyone who would want to follow along, yeah, please do. But essentially, I'll be coding on RStudio, but the notebook is I've just sent it. I have a liking to RStudio, so yeah, I will use RStudio. So I think I'll is my screen visible? Maybe.
Yes, I can see it.
Okay. Okay. Nice. Huh. Yeah. Hello everyone. I hope it's a bit better now. So I'll just quickly go through an example of solving a polynomial regression problem in R. So just as Steve said, sometimes our data doesn't have a linear relationship, but we still want to predict an outcome. So I'll just be, a linear relationship where, as Steve has said, they're directly related. Y is equals to bx, where b maybe is a variable. Sometimes, in the real world, things don't always go as planned. Just like now, a polynomial regression could really help us in making a prediction from nonlinear data. So for polynomial regression, what we had planned in doing both in R and Python is looking at a data set of analyzing internet traffic over the course of the day. So even from the problem itself, it's really hard to to try and predict the internet traffic at each hour, because things change. So that's a really nonlinear relationship. Yeah. So as always, as Steve said, always begin your machine learning process by just having a sanity check on your data, seeing how your data looks like, plotting it, yeah, and before even you decide the type of regression model that you're going to use. So so there are these two packages here in R that we're going to use today. That is the tidyverse and plotly. So also Python people, I know you're very used to plotly. It was first, I think, implemented in JavaScript, and then Python, and then lastly R. So it's a really good plotting package that gives interactivity to your data. And then there's the tidyverse. So the tidyverse is like a group of packages maintained by RStudio. So that helps data science process, I think, fun. I like to say fun and easier, and yeah, and brings sanity to your data science process. So I think I'll just start off with it by loading the packages. So maybe in case if you don't have these packages, you can have them installed as maybe later install the packages concatenate tidyverse and plotly. Nice. So as I said here, plotly is not compulsory. It's just a package similar to ggplot, our typical plotting package in R, but it really helps to bring interactivity to our plots. So, and then I'll load the data. So in the link I've provided, there's you can find the data there on the Azure notebook. So I just downloaded it and I'm loading it on my end. So this is just loading the data, the path, and yeah, it's a CSV file. So let's come and see. Let's see how our data looks like. So we do this using the view command. So the view internet traffic, how we have called our data, and yeah, basically this is how our data looks like. For each, we have an hour. Maybe this is 12 a.m. and then 12 a.m., 1 a.m., 2 p.m. up to 24 hours. And then in each row, these are the columns, and then in each row we have like the day. This is day one. Day one at 12 a.m. The internet traffic was 43 gigabytes per second. At day two, at day three, at day four, at day five, at day six. So it's a really small data set. Drive the points home, and yeah. So in R, or anyone, if you are in R or want to venture out in R, this is not the typical type of data we want. We usually like more tidy data where maybe all these columns of the time will go under a single column known as hours, and another one known as internet traffic, as we'll do in just a minute. So, and then another way to do a sanity check on your data is to see the structure of your data. So using the structure command, so structure and then the data. And then as it is loading up here, you can see that the data is a data frame. So a data frame is like an Excel sheet-ish with 6 observations. So the 6 observations means the 6 rows, as you have seen, each representing a day, and the 24 variables. The 24 variables are the hours. Okay, so this command here, any NA, it's called any not available value. NA means not available. So we're checking if we have fields in our data set that do not have any values. So if we do that, we're told false. So it means our data is complete. In other data sets, we'll have missing values, and we'll discuss that much later, how to solve such problems. So this is a really strange data set, as I've said here. We have 6 rows and 24 columns. This is not the normal format we're used to in R. So currently, and with the hour, which is the hour spread across multiple columns. So preempt what I'm saying. This is give me a minute. So maybe to preempt what I'm saying about the tidy and the tidy data set and untidy data set, eventually we want our data set to look like this, such that all the hours are under one column and all the traffic are under another column, and then the observation of the day is in another column. So this is what we want to do. Want to play around with code and transform our data set from this wide format to this long format, which is more amenable to apply a polynomial regression. So let's get right into it. So I mean, this is usually basically the process of any machine learning algorithm. You first have to make your data into a format that supports the machine learning algorithm. So so we need to reshape the data using a package called tidyr, using the tidyr gather function, so we can plot our data using ggplot2. This is because ggplot2 expects our data to be in long format. So these are the stuff you're likely to face, in the real world, transforming your data into a format accepted by subsequent operations. So I'll just start with it. So maybe for those who have never used R, this is known as the pipe operator. I think it's like the dot in MATLAB, in Python, I mean. So what it really does, it takes the data on the left and passes it to the function on the right. So for instance, internet traffic, I mean, this was our original, this is our data set. It's this. So I mean, it's this. So what we're doing here, we're taking internet traffic, and then we are passing it to a function called gather. So what are we doing really here? What we're doing here is that we're telling gather, we're taking internet traffic and giving it to the function gather, and telling it any column, put all the columns under one column known as hour, which is the key, and their subsequent values, put them under another column known as traffic. So simply that is what we're doing. And I'll try and show this sequentially so that maybe to drive the point more home. So I'll use the view command, and then I've just pasted these commands here. And when we do this, voila, what have we done? We have done basically what I had explained. We have taken all the initial columns in the internet traffic, and then so the initial columns were this 00, 01, 02, 03, 04, and then passed them into a new column known as hour, and then their subsequent values, we have put them in a column known as traffic. So that's one way. So the next question we should be asking ourselves is, how do we also account for the days? Because here we don't know what date is. At least here we know the first row is day 1, second row is day 2, third row is day 3. So how do we account for the rows? We use the function mutate. So what mutate does, mutate at its core creates new columns and does transformation to existing columns. So here, mutate observation is equals to as dot factor repeat 1 to 6 24 times. So let me just run this, and then I'll explain what it does. Yeah, so basically what have we done? We have, as I said, mutate adds columns and also does manipulations to columns. So so I've taken mutate, and then I've made a new column known as observation, which is here, a new column known as observation. And then in our original data set, we had 6 days. So I'm just doing a simple trick that says repeat, from 1 from like our 12 a.m., repeat a number 1 to 6. So 1, 2, 3, 4, 5, 6, and then repeat it again 1, 2, 3, 4, 5, 6, 24 times. So why 24? It's because it's 144 divided by 6, and then you get 24 times. So basically, it's just repeating, the days 1 to 6, 1 to 6 to represent each day. As factor just means these values are categorical. So a 1, maybe if I filter here, a one for 1 day, can be accessed in all the 24 hours. So for day 1, these are the values of internet traffic across all the hours. Day 2, yeah. So that just wants to drive the point home of having an hour, of having that each digit from 1 to 6 represents as a particular day. So I'll run that. So here mutate if, just here we just say mutate. If there's any character, put it as integer because you're dealing with numbers. So this is just like a how do I say, like a safety mechanism, just to put your data in numbers because you're dealing in numbers. So this head function displays your newly obtained data with the number of rows you've specified. So we said 8 rows, and that's what we've done. So at least we have done the data transformation part. So we have moved from a data set like this to a more friendly data set for manipulation, which is this. So we have moved from this to this. So yeah, that's at least that's progress. So from now on, we can really start the trying to fit models. So as Steve said, we need first to graph and see how our data looks like. So just preempting it, this is how our data, because although our long format of data is neat, we really have no visual representation of how things look like. So here so in this part, it's just trying to make simple plots. So I'm taking the new data that we formed, traffic by hour toll, and then so I'll just do this so that then I'll just really explain it quickly. So I'll do it just step by step. So as I said, this pipe operator takes the data on the left and puts it on a function on the right. So we take the data we have just formed, traffic by hour toll, which is this, and then we pass it to a plotting function. So ggplot is a function, and then we'll wrap it in plotly. So when we plot the first step, which is basically building an XY axis, as you can see, aesthetic X is the hour and Y is the traffic. So now we have just built a simple, like a canvas. So it's now you to play around with it and make it your own. So thank you, Hadley Wickham, for this. Hadley Wickham is the one who wrote this package. So yeah, I'm a big fan. Anyhow, so let's add geoms. So geoms are defined what type of graph we want. Maybe we want a line graph, maybe we want a scatter plot, maybe we want a bar plot, but for here we just want a line graph. So we have traffic and hour, and then we want a line graph for each day. So we want to see for the 6 days how the traffic fared for each day. So we ask ourselves, if we just plot everything just like that, it won't look good. So how do we differentiate each day? So that is where these aesthetics come in. So this is an aesthetic. It helps us differentiate different parameters of data by adding stuff like color, shapes. So what I'm saying here is give me a line graph where the color is mapped to the observation, and observation is the day. So each day will have a different color and a different line type. So if we do this, should expect, yeah, something-ish. Something, yeah. So yeah, so this is what we get. We get, as you can see here, day one is color red, day two is color, I think, green. So good with colors, and different line types. And then this other stuff basically adds, basically, how do I say? This is just renaming the x-axis. This is renaming the y-axis, adding a title, and then putting the title at the middle. Yeah, and then as you can see, this is the ggplot package. But if I run this piece of code where I've wrapped our figure in ggplotly, we get like a nice interactive graph. My computer is loading a bit. Come on, come on. Nice, nice. So we get, this is what we get. This is what Steve was saying. First, plot your graph. First put your graph in. Put your data in a tidy format where you can do operations, and then visualize, see how the trend of data is going. So yeah, so as you can see, this is how our data looks like. And as I was saying, Plotly is really interactive, so I could filter everything out and be left with day one. And yeah, you see, like from 12 a.m. this is how it goes, and then it dips to around 3 a.m. Before sleeping, and then it begins to rise again from 6 a.m. Yeah, maybe at lunchtime I'm expecting to be a little, yeah, at lunchtime it goes down and starts coming again, and then people are going off for work. Yeah, so at least know how your data looks like. So given this data, we can say we cannot use a simple linear regression, because a simple linear regression just draws a straight line through the data. So a straight line will not be able to will not be able to fit our data well. So here we result, and also a multiple linear regression will not also do the trick. So in this instance where the data is so like unpredictable and so nonlinear, that's why we adopt a polynomial regression. So here I've written code for writing the same graph, but in Plotly, exclusively in Plotly. Maybe for those people who use Plotly, because here I've used ggplot and then wrapped it around Plotly, as you can see. But here it's purely in Plotly. I hope so. The Plotly syntax, I think it cuts across all the three languages: JavaScript, Python, and R. Yeah, so yeah, this is basically that. And then as you can notice, the data it looks so compact. We have so many things that are lying on each other, so many hours. If we can put everything, yeah, you cannot really get a clear observation, in my opinion. So yeah, this is known as overplotting, and I've said here we should summarize the data to help us visualize trends. So overplotting describes situations in which multiple data points overlay each other within a plot, causing the individual observation to be non-distinguishable. So what will we do? We'll visualize clearer pattern by taking the average values for each hour. So what I'm saying is, maybe for 12 a.m. we do the average of it and get a value. For 1 a.m. do the average of the 6 days and get a value, and see how it will look like. So basically, this is what I've done here. I've taken our data set. I'm creating a new data set called modified traffic by hour toll, and then I'm grouping by hour so that all operations are performed hour-wise. So if I'm doing an average, every operation will be performed in a given hour. And then I'm just doing a mean. I'm just doing the mean for, maybe if it's 12 a.m., I'm doing the mean for all these six days. Yeah, so that's that's what I'm doing here. And then after that, I'm plotting the hour versus the traffic mean. So let's see how it will look. So the plotting functions are still the same as the one I used before. As you can see, the syntax is just the same. Yeah, but now here I'm plotting the average. So at hour 0, the average is 1 a.m. lunchtime, the average is 38 Gbps. Yeah, so this is better. This gives out maybe a clearer and more neat approximation of how our data looks like. So this is, as you can see, it's kind of an S-shaped that is slanting. So yeah, so that is why we do the average, so that you can get a clearer uh, visual display of what our data looks like. And yes, and now I think after that we can now go into the finding the polynomial regression. So here is just a bonus where you can try and plot box plots. So this is really not dwelling to it. A good way of seeing how the data like behaves. It gives you a minimum, as you can see, a minimum, a median, and a maximum. So yeah, these are like exploratory data analysis where you really want to know what is my data telling me before you can actually implement any machine learning algorithm. So yeah, we're finally here, and now we are what did I say here? Let's use the midpoints in between the hours. Okay. So the LM, linear model function in R, allows us, together with the polynomial function, allows us to fit a polynomial regression in this data. So as Steve said, the degree of polynomial, basically, in very simple terms, it determines how curvy your line is. How curvy? How do I put it? Yeah. Can my model try and fit the shape of this data? That's why you play around with the polynomial degrees. So as Steve said, I'll use the forward selection where I'll just do approximations. I'll start with the first degree, which is basically a linear model, second degree, third degree, and see which one does justice to fit my data, my S-shaped slanting data. So so here I said you can use LM directly, but for this exercise, I'll do it using, in this exercise, I wanted everyone to see how the model is fitting the data. So what I'll do it like visually. I'll show you, this is the model, this is the polynomial model you fit, and this is how it fits our data. So I wanted to do it, there's a way you can do it directly, but I think to drive the point home, we'll do it visual. So sorry for the Python guys. Please bear with me. I'm about to finish. So this is the plotting function, as you can see, where we take the modified hour traffic. So did we see the modified hour traffic? This is how it look like. Yeah, hour traffic observation, the observation of the day, and the traffic mean. So as you see, this is how we did the traffic, as I was saying, the traffic mean. So this is like for 12 a.m., we do the mean for all the 6 days, 1 a.m., the mean for all the 6 days. So yeah, the mean is basically the same as you see here. So what am I doing here? I'm saying take the modified hour traffic and then plot it, and then I mean pass it to then we read this as then. So take the modified traffic by hour 12 and then pass it to ggplot, our plotting function. So in ggplot, you're telling ggplot your x-axis will be the hour, and your y traffic and your y-axis will be the mean, will be the traffic mean. And then here we're using geom point. So as you can remember, the last time we used geom-line. So geom-line says line graph. So geom point means a scatter plot because you have point, 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 small dots. And then this is where we implement the polynomial regression in visually. I mean visually. So we take this geom. It's called geom smooth. What makes geom smooth and geom line different is that geom smooth, you can, how do I say, you can, it's okay. As you can see here, it's written smooth. So that means it can bend ish. I don't know if that's the right word, depending on your data. So as going still back to Steve, we want to find a model that can fit this data, that can curve to this data set. So that's why we use GeoSmooth, because it has that feature. And then you can specify the amount of curving by using a formula. So here the formula is LM. So LM in R, when you don't know anything in R, you just type question mark LM, mark the function. So LM is basically packages that help you fit linear regression, which help you fit regression models. So that's what you're telling GeoSmooth. So you're saying GeoSmooth, you use this package that we use to fit linear, that we use to fit models, and then in it you use the formula of polynomial regression. So what is the formula? So the formula is, you're predicting y. Y is the traffic mean. You're predicting y given x, and x is the hour. So you want to predict the internet traffic at a given time. That's what we're really doing. We want to predict the internet traffic at a particular time. So in polynomial regression, we're trying not to determine the degree of the function. So here we started with degree is equals to 1. So that basically is y is equals to maybe ax. Where the x variable has really a power of 1. So the degree of polynomial is 1. And then I've just said the GeoSmooth to have a color of gray and to be dashed. That's basically, in simple terms, what this is saying. So let's see how this will look. Let's see how this will look. So please don't fail me. Yeah. So this I hope it's visible. I'm really echoing what Steve said, because he made a really good introduction. A polynomial of degree 1 is a simple linear regression, just fitting a straight line through the data. So as you can see, this is not it will make, this is a really bad model. If you used a polynomial degree of 1, then you'll be getting all sorts of wrong answers, not even correct answers, wrong answers, because it's really not fitting our data. So what do? We do a trial and error to find GeoSmooth that will help fit our data. So let's change the degree of freedom to 2. As you can see, I've changed the degree of freedom to 2. I mean, not degree of freedom, degree of polynomial. So it's a little bit curved and still not doing well. So this is trial and error depending on your data. I'll change it to 3. Wow, yeah. Nice. So 3, I mean, let me change the color to blue so that maybe it can be more visible. Yeah, I hope now it's more visible. So a 3, it tries to approximate our data, but not so well, but it's trying. So we just go on. Yeah, okay. Four is pretty good, as you can see, but misses our data here and there. And yeah, let's say it's a good trial. It's a good trial. And let's see how 5 will look like. Okay, 5 also 5 could be a good degree of freedom. I mean, could be a good degree of polynomialism. So, but not really, does not really fit our data as you expect, as per the black dots. So I've gone to a 6. Yeah, and a 6 tries, yeah, as you can see. It gives a good generalization. So let me see 7, if there's a change in 7. That's not much difference, but yeah. So what we're really trying to do is we're just trying to get a model that will generalize our data. We don't want a perfect model, because a perfect model will be too good in this data, and then it will fail to work on other data sets. So yeah, we just want a good approximation, and I think this is this can generalize any data well. So yeah, so I'll use this. So this I will use a polynomial of degree 6. A degree 6 I think works well for me. You can try others as well, but for this example, I'll work with degree 6. And then after that, I'll just plot this here. If you want the data to, if you want the plot to be more interactive, yeah, you can run that. And yeah, you can play around, just how our data started, and then we added the degrees of yeah, you can, yeah, it's interactive. You can play with it. So yeah, so you see, none of the polynomial functional alpha did a great job in generalizing the data. It looks like the 6th and 7th have identical curves, so I think they'll be a good one. So we can use even higher degrees of polynomial to fit the data, but we don't want to overfit the curve. So we just want a good generalization, because if we overfit, our model will be so good at our particular data, and it will not be good at other data we want to predict. Yeah, so let's see how our six polynomial compares to the real data. So here, basically, I've plotted the polynomial of degree 6, as you can see here. Geom smooth degree is equals to 6 against our real data. So against the internet traffic and the hour of the day. So as you can see, even though it was made, even though we fit the model using the mean traffic, but it still makes a good generalization of the data, and that's what we want. We want a model that not too good and not too bad, just the one fit to make a generalization. So now let's try using this polynomial model to make a prediction of the internet traffic. Maybe we can choose a specific time, maybe 12:30 or 2056, 8:56 p.m. So I've used 8:56 p.m. So now that we have agreed we'll use the 6 model, this is how we save it. So LM polynomial 6 is equals to the linear regression, where we take LM, where we want to predict traffic at a given hour, and the degree is 6, and the data we use to make that model is the traffic by hour toll. So and the data that this model will run on is the traffic by data toll. So we want to make basically this is what we're doing. We are saving this 6-degree polynomial, and yeah, and let's see how that looks. We have come up to the point we use a degree 6, and then we save it, and then we do a summary of how it performs, because I've said save a polynomial regression that predicts traffic by hour on the data set traffic by hour toll. So it did the R² value is 0.85, so it's a good value. Maybe 85%. It tried to fit our data to 85%. So you can try to improve this by using other algorithms such as random forest and everything. So here I'll try and predict. I want to predict time at 2093, I think 2056 at 8 p.m. 56 minutes. And then we predicted using the predict function. So I'm saying T predicted is predict using the sixth our polynomial regression model predicts the internet traffic at this hour, 20.93. You can put it 20.93. When you translate it to time, it will be 20.56. And then let's see how it did. So yeah, our model told us we'll get a traffic average traffic of 54.78 Gbps, gigabytes per second. And yeah, let's see how is that far from the truth. Let's assess it. And yeah, so I've come to the end. So I'll just plot it here. And with what I want to plot is the prediction that our model has made at 8:56 p.m. What will be our internet traffic? Maybe the IT department wants to make decisions. Maybe when do we put on our routers? When do we switch off our switch? When do we switch off some of our switches to conserve power? So and at 8:53 p.m. Yeah, not bad in my opinion. Yeah, not bad. Given at 29, yeah, at 20.93 hour, it was 54.78, the actual value at day one. And here we are getting something 54.78. So yeah, I think it's quite good. Not as perfect, but quite good. And improvements can be made by using other machine learning models such as random forests and some mechanisms such as bootstrap resampling, which will maybe leave it for another day. So that's how you do a polynomial regression in R simply. And yeah, thanks for listening. And maybe Steve, maybe now it's your turn. Thank you so much for listening. And I'll post these materials. I'll send them out to everyone. So yeah, if you have any question, please feel free to ask. So yeah, so Steve, maybe on your end in Python.
Okay, let me try sharing my screen.
Yeah, Steve, I think we can finally we can
Yes.
see them.
Can you
Yeah,
see me?
yeah, I'm so happy for you. Yes, I can.
So I actually uninstalled Teams. I guess there was an issue with my laptop.
I'm so sorry. I'm so sorry.
I couldn't actually see the slides that you are sharing via my laptop, so I had connected to two devices, my phone and my laptop too. It's okay.
We all improvise. It's allowed.
Yeah, sure,
It's
sure.
allowed. But I'm so happy
Great.
things now are turning out great. So yes, so it's your turn. So the floor is yours. So maybe anyone with a question, maybe in the meantime, Steve, as you try and load everything up.
So it's actually loaded.
Yeah.
So was there any question for Eric, or should I just continue?
Okay. I think just continue. Maybe we'll gather all the questions afterwards. I've seen you have tried answering some of them in the chats. I'll try and do the same. Oh, someone asked, please, Steve, please share your notebook link.
Okay, yeah, I shared it and I've made it public so they can access that.
Okay, you shared it in the chat. Okay,
Okay, yes.
yeah. Please
Or I
continue.
shared it.
I'll
Okay, thank you. So basically, as Eric was presenting, I don't normally use R for machine learning, so it was a bit difficult for me to know the commands or what he was typing on the screen. But I know plotly and dash. I've used them. Okay, so getting here, there are different libraries that you need to import. Pandas, NumPy, matplotlib, .pyplot. So pandas basically they're used for reading data and manipulating, removing columns and adding. So NumPy is used for matrix. So NumPy is used for matrix transformations and so. So I just used these three, and actually, as I can see, I didn't need to use NumPy, so you can get rid of it, but it's okay. We normally import them. So here's how we import the data using pandas. So I imported pandas here as PD. So data set is equal to PD dot read underscore CSV. Then here's the data. So let me just show you the data here. So can you see this? Can you see the data, Eric?
not yet. I think it's still loading. But
Okay.
yeah. Now I can see it.
Okay. So I didn't have much data because it's just the beginning and just to show how polynomial regression works. So I just use simple data here. So basically, after reading the data and giving it a variable as data set, we can read or maybe we can see what the data is like by running this dataset.head. So maybe you named your dataset in any other form or in any other variable. You can just type in the variable.head with these braces so that you can see some of the data, actually the top part of your data. So I didn't use the commented part. There was something I was testing in here. So this shouldn't be working. It's okay. Okay, here is our data set again. So then we normally deal with X and Y variables whenever it comes to graphs. So we have an X variable and a Y variable. So we'll have to give them the values or assign them the values from our data set. So as you can see, here we only have position, level, and salary. So what I just did was that I used salary to get the level. So at 45,000, that's level 1, 2, 3, 4. Because we normally deal with numerical data, you'll have to change any categorical data to numerical whenever you need to fit it into a model. So I couldn't use this because it starts from 0. And also that's the index. So this is the index part of that data. So I can't use that column. So I said X is equals to dataset. So the dataset dot iloc. So that's the index location. one, okay, 1 column 2. So that means we only pick the first column. Okay, this is 0, 1, 2. So this means this is it's the second column because Python actually starts at 0, counting at 0. So this is the first. So giving it this range, 1 to 2 means it will just pick the first value because Python doesn't pick the last defined value there. So then again, dataset is equals to, okay, y is equals to dataset.iloc on the second or the third column. You can just call it second according to Python, or according to you how you can read the data or interpret it. That's the third column. So you get their values. So you've stored this data into X and Y. So I've actually not been running the cells. So let me just run them. I'm using Azure Notebooks. So yes, you've used that, similar to Jupyter Notebooks. And it's actually quite simple to use. Still importing the data. Just a moment. So the good thing with Azure is that the Azure Notebooks is that you don't need to install these libraries anywhere. They are pre-installed and you can actually get to compute very large data sets in here without the need of worrying your computer doesn't have a GPU if you are taking deep learning and so. So you just run using the shift and enter key. So I've just assigned this. So it just gets to the next cell is the cell. So after that, as I said, best whenever you're given any problem, you first visualize your data. So you have the data set. So you have PLT. This is matplotlib.pybot. I imported it as PLT dot scatter. Then you have the data set position. You want to get the position column and also the salary column. So then you give it a title and you give the x axis a label, so job position, and the y axis a label, the salary expected. So that's what I used here. Then I plot plt.show. So basically this means position should be on your x coordinate, as you can see, because it's the first one there. So then again the comma, so it's like x, y. So the y salary should be on your y coordinate. So then I read this. So you want to know the values of y where it runs. So the type should always be an array. If maybe you have a list and you try to fit it into a model, you'll get an error. So that's the reason why I use iloc here, because it should be taking it as an array. So if maybe I was to take it just you can also assign it like this. So x, small x, data set. Then you take the column. You can assign it like that. However, this should be a list, so it should be giving you an. So that's why I use iloc, so that it can be converted directly into an array. Python is a bit sensitive here with the models. So also the X is also an array with these values. So the values, here they are, 1, 2, 3, 4. So this is the level. It's actually representing the position using values, numerical values. So that's why you're seeing 1, 2, 3, 4, 5, 6, 7, 8. So another thing, and maybe I can add, whenever you're given any problem to solve, any machine learning problem to solve, you try to get as many columns as possible, because you'll be improving on the features and also basically the accuracy of your model. So here we have sklearn, popularly used, and here I imported something called train test split. So it's used to split the data into two, like telling it, okay, so from sklearn.model underscore selection, import train underscore test underscore split. So X train, so you have an X train, an X test, Y train, and also a Y test. So X train, X test, Y train, Y test is equals to, so this is the function that you imported there. Train test split X, then you give it, these are the values that we had up here. We had already defined them here with the values. Yes, you can see that. So you're splitting that data. Then the test size is 0. So that means you'll be using 80% of that data to train the model and only 20% to test your model accuracy. So this is random state. This means that it shouldn't be running that data. So whenever you run this cell any other time, it should be selecting the values in a different manner. So it should not cram the data. So because if it crams the data, so it's like just a kid. So whenever it crams something, it will definitely affect the model accuracy because it will overfit. So it printed the white train here. So then we want to do some linear regression here. So sklearn also has linear regression included in the libraries. So it's like a class. So this is the library, sklearn.linear underscore model, import linear regression. So then again, we initialize that class with our own variable. So I just chose linreg to represent the linear regression. So then again, we fit X and Y. So it's like fitting that data. Here we can choose to use X train and Y train, but because I didn't have much data, I just used the entire data set to fit into the model, but we are supposed to use X train and Y train. So I use the entire data set so that you can see the values quite well. So after doing that, we'll need to visualize the model or the results that we get there. So I define a function here. So we use matplotlib, and we are telling it that we want to plot X and Y with the color red. So the values, so here are the values. So the values that we had initially, so the 45,000, the data sets that we had, we want to plot it as we had done earlier here. Yes. So then again, we plot the predicted, okay, it's the line. So the prediction, or maybe the line which will be used to make the predictions. So we have the X, and also we predict the X. So this is the Y value, because we'll be feeding into this model X value so that you can get the Y value. And the color is blue. So as you can see here, the line. Then you give it a title and also an X label and a Y label. So then again, I type in this. So plt.show, it means now you can visualize that data. So this is the function. So then we call it here. So this is just calling the function so that you can get the results. So as you can see, here was our data. So you're able to see where I am. Eric, confirm that.
Yes, Steve. I can see where you are. I'm following.
So which cell are you seeing? Are you seeing the diagram?
Yeah, the one with the blue line.
Okay,
yeah.
Yes.
I can see it. Okay.
Thank you. So this is the linear regression part. So as you can see, these are our data points, and this is our predictor. So it means it hasn't utilized these points to create maybe the best function, which can be used to predict something. So we'll be predicting the salary that someone can or we will be getting depending on their position. So with that, we now decide to use polynomial regression. So also scalar has some features, some polynomial features. As I told you, polynomial regression is also a linear regression, but it's added. There are some features which are added. So we import them, and we have this variable to initialize the class, that is the polynomial feature, and also we give them the degree, so the degree that you want. So the first degree, second, third, as I was telling you, x1 squared, x1 cubed, x1, yeah, raised to power 4, yes. So then we have an x polynomial. So this is the x polynomial. So we are fitting in. So the poly, okay. Just a minute, there's something I need to show you. So this is actually a class. So it's the polynomial function or the polynomial class, which I initialized using the polyreg. So I'm not seeing where this cell is. Let me just check on it. Yes, I dropped that cell whereby I was initializing the polynomial regression class with this polyreg variable. Then I fit it into I transformed the x values using the fit transform function so that I can maybe have the degrees. Okay, so actually it's here, yes. So the polynomial regression, then I called the class. So it's actually a linear regression function because we had already imported it up here, yes. So it's just a matter of initializing with another variable so that it won't affect the one that we had for the linear regression. So then again, I fit into the x polynomials and the y now. So then this is the function to visualize what we've done, and also having the line. So you get a scatter plot to scatter the x and y coordinates for the values that we had, and we define the color also as red. So then want to plot x, then the prediction. So the prediction is done like this. So the polynomial pol reg dot predict. So we call the predict function. Then again, we have it into, okay, we add onto that polyreg dot fit transform x. So these are the x polynomials. So you can just use x polynomials here if you don't want to use it like this. Then again, we define the color as blue. We define the title, the x label, the y label, then we show. So then we call the function, and as you can see, so it's a bit better because it's touching on most of the points, having the fourth degree. So we'll change and you'll see what's the effect. Let me just call this. Okay. Oh, I see this. This was the issue. I'll need to initialize that class because it's seeing it as a linear regression. So just a minute. me kindly restart this because some cells had not run. So yeah, I'd made some changes. So as you can see about the data points, so we can just change the degree and see what changes. So as I said, and as Eric maybe did earlier, you can see this is the first degree and it's just a simple linear regression. And have it as 2, still not getting all the data points quite well. So you change. So this is forward selection, as maybe I mentioned earlier. So the degree 4. So that's what I used. And here the polynomials. So this is normally generated by itself. Okay, it's just doesn't change, so it's static. So then you can see quite well about the data because we don't have much data, but this is the square root. Oh, okay, the square of this. So also this is the cube root of this. Okay, I'm saying cube root, sorry. It's raised to power 3 of this. So this is raised to power 2 of this. This is raised to power 4 of this. So that's how it works. Okay, we want to predict something here. So here are the levels that we had, 1 to 10. Now we want to feed it 5.5 because it's not in here. So you can just feed it here. So using the linear regression, so we predict that. So 5.5. So this is the output. So this should be the salary. So it's not quite good. It's not quite impressing about the predictions because as you can see here, it's like above this line. So using the polynomial, I'll need to change this. So there's an issue with this function here. Just a minute, rectify that. Oh, here actually. Yes. So this is the output, and you can see it's like normal to have that 132, 148. So having this level about 5.5 here. So the prediction is it's okay. So this prediction should be changing if maybe you change the degree. So now we want to evaluate our models. So using different, okay, I used R square as the matrix. So you just import the matrix from sklearn. So then you run it. Okay, let's just see. So linear regression has 0.9205. So, and this should be close to 1. So it should be tending to 1. So this is the variance. So the variance, having a variance of 1, it means it's like 100% accurate, and that's not quite good because most of the time it might have overfitted or crammed the data. So then the polynomial regression part, it's 0.98. So you can see there's a change. So this is a very big difference according to machine learning models. So there's a huge difference here. So that was Python. I'm sorry, I changed some code in here in between. So that's why some code was not running, but it's okay. So if maybe you have the link, because it auto saved, you can also get the same. So Eric, I think I'm done with my presentation. Anyone with a question?
Uh, Thank you so much, Steven. It was really nice seeing how you can do it in Python. On my end, speaking for myself. So yeah, thank you so much for making it look easy. I think yeah. So I think someone
Yeah,
some,
it's quite easy for you. The functions that you are running, they are a bit complex.
no, basically I think
So
it's the same thing because
and also we don't have much in Python. So you just get the data, load the data, you split the data and fit it onto models. Although having these models as like this, just calling it like this without fitting in some features, it's a bit okay. I can see it's not that accurate. So you can maybe change and see on your accuracy.
okay. Steve, hello.
Yes, hello.
Yeah, nice. Yeah, so I'm just waiting for questions maybe in the chat from the audience maybe. With a question.
Yeah, I'm also checking. So I've rectified the variable names that I had used earlier because they were a bit similar, and so I had to change some of them so that you're not that confused.
Okay. Thank you for doing that. Thank you for doing that. And so maybe a quick question. or maybe observation, we we did polynomial regression because it's more realistic, right? In the real world data.
Yes.
Okay, okay, yeah. So yeah, so just speaking that out. Yeah, and guys, I think yeah, I think
Yeah,
please
most of
please
the questions. And also, most of the questions that maybe you might come across, they'll fall under that.
okay,
So most of
thank you.
them are supervised machine learning because we already know what you want. So that is the Y value. So it's just a matter of checking on it. So which is the best model that you can use to create graphs so that you can predict that. So when it comes to maybe something like reinforcement, it's a bit tricky. And the planning, yeah.
Okay, so thank you, Steve. Thank you, Steve, for that. And David had a question. So I'm like waiting for him to unmute or something. Please, David,
Okay.
the floor is yours.
Hi, Eric and Steve. Can you hear me?
Yeah, yeah, loud
Yes.
and clear, David.
Okay. I wanted to ask Steve. You said that like the R square variance of 92 is very high for the model, which is the optimal variance that one can get, so that can try to use the model for prediction analysis.
Okay. Thank you for the question. So what variance is, it's like you have the prediction, so you're trying to get how much is it varying. So because you are dealing with values below 1, it's squared, so you get the R square. So squaring it means it gets a bit high, and as you can see for the linear regression, which wasn't that good, it was 0.92. It wasn't that pleasing, and you can see the variance was a bit high. So simply because you're just squaring the values that you get. So I can't specify on the best variance that you can have. So the best variance should be, okay, let's say 0.99. But in most cases, you'll find that that model is overfitted. So having an accuracy of 95 or 99 point something percent means that model has actually either overfitted or has crammed the data. So, but normally try keeping it between 0.95 and above. Also, that's not the only metrics that you can use. So there are various metrics that you can use to calculate your accuracy. So you can use different methods so in one model so that you can see which is the best that you can use and compare those so that you can get the actual model performance. Yeah. The question answered, David.
Yeah, yeah. Thanks for that. At least you have explained it better. I understand.
Okay, thank
Yeah,
you.
Thank you.
yeah. Maybe
Shekra,
adding up to Steve maybe a bit. The R squared is just a coefficient. So as Steve said, in case that your regression model is almost perfect. Yeah, so it's just a measure of how good your model is doing. And then you can also check on stuff like the mean squared error. You can also look at it either from accuracy or from an error point. So from accuracy, you use the R squared, and from the error point, how the error margin or the error matrix, you can use the mean squared error. Yeah.
Okay. Thank you for that.
Okay, also there was something that I mentioned here. So I've added some footnotes, and you can get to know the difference between the loss and the cost. So I'll also share the slides with you. So I'll just upload them. And maybe if you have any other question, you can be in contact with me or Eric, and we can sort that out. So also there are various metrics, but we are not going to touch on that today. Maybe that's a topic for another day because it's a bit wide. So Eric should be maybe hosting another event for that. So it can be actually about 2 hours for the metrics. Yes. So depending on the language too.
Okay, thank you, Steve. And how can one reach you?
Let me just type in my phone number and also my mail.
Okay, I'll appreciate.
Yeah, so as Steve writes, maybe anyone with last call, last question, maybe we want to wrap it at here, to wrap it up at here. So, yep, pardon?
I have a concern.
Okay, yeah, true.
That's not your mail.
Oh, yeah. Oh, stuff were changed. It's okay. This has okay. I'm also writing down my email, eric.wanjao at studentambassadors.com.
So did you get mine?
Yeah, I got yours, and I also see the phone number. So please, anyone, or if you'd want to be added in our AI/data science group on Teams, please contact either Stephen and I, and we'll add you in 2 shakes. So I think we'll wrap it up at there. I want to say a big thank you to everyone who attended and stayed during the R session and the Python session. We hope now you have a basis of regression. So we'll do more. We'll go further. We'll go advancing. Maybe next time we'll do maybe classification. The next time we'll do deep learning. Oh, yeah, we'll keep you up to date. And yes, so and also want to say a big thank you to Steven for persisting even when stuff did not work out as well. So thank you so much, Steve, and it was a really big pleasure doing this with you. And thank you everyone for attending and for your interest. We'll be sending out the materials in a short while, both for the art, the Python, and the slides. So maybe Steve, one last word, and then you can close the meeting. Thank you so much, everyone, on behalf of the Microsoft Student Ambassadors here in Kenya. Have a good evening.
So as I was saying, yeah, I was a bit held up, and you know that, but it's okay, you've done it. And also, I can maybe urge everyone. So if maybe you're learning something new and maybe you'd like to present, that's actually the best way to learn. So I learned that while taking my I ran various clubs at school. So I learned that while I was taking my IoT stuff, because I had to prepare quite well before I present, and you actually learn better on that.
Steven?
I've shared the PPT, so I hope you got them.
Hello, Nashipai. You were saying something, maybe?
Oh, thank you, Eric. I'd like to say thank you because personally I've learned so much, and nobody has I feel like it's nice to appreciate the people who take their time and actually prepare to make us learn a new thing. So thank you. We really appreciate.
You're welcome. So, as I was telling Eric, I was a bit held up. I'm an instructor somewhere, and also I have some certifications to take.
Okay,
So,
everyone.
Eric,
Thank you.
thank you for the session, and
Yep.
everyone have a good night.
Yeah. Have a good evening, everyone. Thank you so much.
Okay, thank
We
you.
hope to see you soon. Okay.